Hello everyone, welcome to Econ 3040 Computer Lab number 3. This computer lab may be found in Learn under the R Computer Labs section. In today's computer lab, we are going to be exploring the multiple regression model using the CPS, or Current Population Survey dataset. First thing to do, of course, is to open up RStudio and create a script file. I will click File, New File, RScript. And the next thing we want to do is get our data. I will copy and paste this command, which reads a .csv or comma separated value file from a certain location. And that location is typed in quotation marks inside of this brackets. Now, your file could be located anywhere. It could be on your computer. It could be a different location on the internet. You just need to appropriately change the location of the file that you want to input into RStudio by changing this path that's highlighted right here. All right, so I will run this command, and we see the dataset pop up in the top right corner of our RStudio. We should, of course, take a look at this dataset to begin with. I will click on the spreadsheet icon next to the dataset to get a little bit of a description of what's going on inside of this data. So each column is a different variable. We've got wage, so that's the wage of the worker, the number of years of education of the worker. We've got the work experience, the age of the individual. So all of the variables are arranged as a different column. And then each row represents a different person in this data set. So row 1 is person number 1. And the entire row tells us all the information we have on that person. So we know that this person made $5.10 per hour. They had 8 years of education, 21 years of work experience. They were 35 years old, and they were Hispanic, and so on. Now, the ordering of the observations doesn't matter. It's random. So there's nothing special about person number 1. They could have been person number 36 or whatever. All right, well, let's notice that, first, what data set are we working with? Well, this is from the Current Population Survey in the US. This is a very famous data set and a very popular data set that collects labor and demographic information on people in the United States. Now, we're using kind of an old version of this dataset from 1985, but that's okay. This is a famous version of the dataset that is being used for many educational purposes. Now, I could have used, instead of clicking the spreadsheet icon, I could have typed View CPS into RStudio, and I would have obtained the same result. I would have been able to see this spreadsheet here containing all the data. All right, now let's think a little bit about some of these variables that are character strings. So notice that many of the variables do not contain numbers, but they are instead characters or words. We've got lots of them in this data set. We've got ethnicity, region, gender, occupation, sector, union, married. This is very typical of a data set. They're not numbers. The variable values are not numbers. They're words. But in order to use them in our statistical analysis, we're going to need to transform these words into numbers. And you may have guessed it, the way we're going to do that is by creating dummy variables. Let's look at the ethnicity variable, for example. It turns out 3 different values. It takes on the value Hispanic, or CAUC, that's short for Caucasian or white, and it takes on the value other. So those are the 3 possibilities for this variable ethnicity. It just identifies the ethnicity of each worker. They're either Hispanic, they're white, or they're just any other race. Now, in order to use a variable such as ethnicity and any of the other character strings, any of the other word variables, we need to create dummy variables from them. So for the ethnicity variable, for example, we would create 2 dummies, even though there are 3 categories. And the reason that we only create 2 from 3 categories is in order to avoid the dummy variable trap, which I'm not going to talk about in this lab, but it is an important topic in this course. Now, luckily, R will recognize that variables like ethnicity contain several categories. So R is going to recognize that this is a categorical variable. It's assigning each person in the dataset to a particular category. R will recognize this, and it will automatically create the system of dummies for us. And to see this in action, let's just try running a regression using one of the categorical or one of the word variables, ethnicity. I will close down my spreadsheet, and then I will copy and paste this command into RStudio, and let's run it. What do we get? Well, you see down here that, first of all, I'm sorry, what are we doing? Well, we are choosing wage as the left-hand side variable. In this lab, we're going to try to explain the various factors that lead to differences in wages among workers. Now, ethnicity might be one of those factors. So we have, on the left-hand side, we have the wage variable. That's our Y variable, or our dependent variable. And then on the right-hand side, we have the ethnicity variable. That's our X variable. But actually, it's going to turn into 2 X variables. But R will take care of that. Now we look down here, and we see that we have 2 X variables in the regression. Ethnicity Hispanic and ethnicity other. There's no ethnicity Caucasian. That dummy variable has been dropped from the regression. And it just becomes the base group. So now we are comparing the wages of people who are Hispanic and of other race to the wages of people who are white, Caucasians. All right, so we've run the regression, and now let's try to interpret these coefficients that we've estimated. These are the estimated coefficients right here, negative 1.9946 and negative 1.2196. How would you interpret these estimated betas? So remember, these are on dummy variables, so it's not a slope. The estimated betas on dummy variables, they express a difference in sample mean. So the way to interpret this is that this is saying that Hispanics make $2 less on average compared to Caucasians. And this is saying, this negative 1.21 is saying that other races make 1.22 less on average compared to Caucasians. So whichever is the base group, that's how you compare, or that's how you use this number to compare the differences in means between the two groups. Now, if you wanted to know the difference, the difference in wages between Hispanics and other races, then you would have to subtract these two numbers. So just from eyeballing it, it looks like Hispanics make 80 cents less on average compared to all other races combined. Okay, so that is how R will end up using a character variable or a categorical variable. And you see that we have lots of them in this data set. If you can see where my mouse is hovering right now, R has recognized that ethnicity is a character, CHR, a character variable, and each of the values appear in quotations. So they're just words, but luckily R is going to take care of it for us. It's going to transform these words into a system of dummy variables. And it will always create one fewer dummy variable than the number of categories. So for example, if we had 8 categories in a variable, if there were 8 different possible words that the variable could take, then R would create 7 dummy variables from that categorical variable. Okay, the main purpose of this lab, or the main motivation in this example, is to estimate the returns to education. And by returns to education, we want to know how much extra do people earn from an additional year of education. This is a very important question in labor economics, especially for countries, for societies where education is publicly funded. We need to know how valuable is an education if we're going to argue that it should be funded. So let's try some models in order to estimate this returns to education. And we're going to start with a very simple model that just includes a couple of variables. And what we are really interested in is this beta 1 right here. This beta 1 is our returns to education. Whatever we estimate that number to be, that's going to tell us how much more people earn on average due to an additional year of education. Why do we need to add other variables to this model, even though I only care about the returns to education? Well, that's the whole purpose. That's the whole argument in Chapter 6 about the multiple regression model. We need to include these other variables because they may be correlated with education, and they may also have an effect on wage. So anything that we think that is correlated, that is related to education, and also determines wage, we need to include in our regression. Otherwise, this estimated beta 1 is wrong. It's biased and inconsistent. All right, so let's estimate this population model. And the way that I estimate this population model in R is by using this command. So instead of the equal sign, we have the tilde sign. And now each of the x variables is separated by a plus sign. So I will just copy and paste this command into my RStudio. And I'm going to run this model. I'm going to run this command. And we see that the model pops up in the right side of our screen. I'll close down this CPS thing. Now here's the model we've estimated. There's a lot of junk in there, but that's okay. And how did I get this model? Well, I ran a regression. So here's my least squares regression. And then I just saved it. I called it model 1. And now it's stored into RStudio and I can refer back to it later. Now let's take a summary of this model. So I'm going to copy this command and I'm going to run this command. And now we see the results of the estimation. We have a summary of the estimated model. What are the returns to education? 75 cents. So this is telling us that a worker who has an additional year of education on average makes 75 cents more per hour. Now, remember, this is 1985, so that would be a lot more today if we were to adjust for inflation. And what else do we have here? Well, this is saying that males make, on average, $2.12 more than females. Now, before we go any further, let's take care of OLS predicted values. This is often useful. After you estimate a model and you want to interpret it, you may want to do this. You might want to come up with a predicted value for a representative case. Now, we've already talked about OLS predicted values. All you do is you plug something into the X variable and you get your predicted value. So that's what we're going to do here, except we're going to use some R code to make it a little bit easier. So I'm going to copy and paste the next command. And now let's take a look at what it's doing. So I'm going to predict a value. And I'm going to predict a value using the estimated model. So that's model 1. And don't worry about this data frame part. You'll just have to follow this syntax. You'll have to copy this when you want to do a predicted value yourself. But inside of these brackets, I'm going to plug in values for the x variables. So what I've done here is I've imagined a person who has 12 years of education and who is female. Let me go back up to the population model here that we're estimating. I'm just picking a number for everything on the right-hand side. I'm picking a value for education and I'm picking a value for gender. And then I'm going to put it in this predict command. And this is what we get. This is our OLS predicted value for a worker who has 12 years of education and who is female. The model, the estimated model, predicts that such a person would make $7.11 per hour. All right, so all we did was plug the numbers into the estimated equation. Now let the usefulness of this wash over you. Whatever model you estimate, you can make a prediction. You could predict something in the future. You could predict what GDP will be next quarter. You could try to estimate a model that explains stock values, stock prices for the last 10 years, and you could try to predict what will be the value tomorrow. So these are all very typical uses of regression models. And yeah, it is very useful. Now, the main topic. Avoiding omitted variable bias. We need to estimate a bigger model. As I mentioned before, we need to include in the regression all the variables that we might think are related to or correlated with education and also might affect wage. So people who have more experience may have less education, right? So if you're 22 years old and you're on the labor market, well, either you've got 4 years of education or you've got 4 years of experience. And so I don't want education to indicate a lack of experience. I need to control for that. So if I see that somebody is 22 years old and I see that they have 4 years of education, well, I'm automatically going to know that they probably don't have much work experience. Well, I don't want that experience. I don't want the effective experience to be working through the education variable. So imagine that somebody does have 4 years of education and they also have 4 years of experience. Well, that's going to be great. And that's something that we need to know. So because these two variables, education and experience, are correlated with each other, and because both of them affect wage, I need to include both of them in the model. Otherwise, the effective experience kind of works through education and gives me the wrong answer for the returns. And a similar argument can be made for a lot of these other variables, but I won't get into it at this point. I'm going to copy and paste this command, model 2, and I'm going to run it. And now model 2 pops up in the top right corner of our RStudio. Let's take a look at what we have estimated. So we will take a summary of model 2. And we're going to see a pretty big, long regression here. Lots of variables in our model now. These are all X variables. And now our returns to education, it has changed slightly. It hasn't changed too much. That's pretty comforting. After controlling for all the other things that may be correlated to education, so these are things that may determine how much education people got and may also determine their wages. After controlling for all of those things, we find that an additional year of education, on average, leads to about 81 cents more in per hourly wages. Now, this is the main thing we wanted to look at, but we could interpret these other estimates as well if we wanted to. It's kind of interesting. It seems that as people age, they make less money. That's maybe a bit counterintuitive. Work experience does pay off. Make about 25 cents more on average for an extra year of work experience. And we can see some other interesting things. It looks like people who work in sales make the least amount of money, and people in the technical industry make the most. Married people make more on average, and people in a union make quite a bit more on average. And that makes sense because unions bargain for their workers' wages. All right, so we did it. We estimated a big model, and it wasn't too painful. Now, we have a question here in the lab. Look at the results, interpret the estimates. We did a little bit of that. Which variables are statistically significant? Well, that's a pretty important question. Now, statistical significance is asking which estimated variables are not zero. which estimated betas are not statistically different from 0. So when we ask if something is statistically significant, we're asking if we have rejected the null hypothesis that the beta is equal to 0. Now we can see that right off the bat using R, just by looking at these stars. Anything without a star is considered insignificant. So, it looks like our education variable is insignificant. This p-value is in fact the p-value for the test that this beta on education is equal to 0. Because this p-value is large, we fail to reject that beta is equal to 0. It looks like there are no returns to education. That's pretty depressing. What things are significant? Well, it looks like the occupation variable is significant. So these stars here are just telling us what value, between which two numbers does the p-value lie. So it's just reading this p-value and saying, oh, this number is small, that's times 10 to the negative 6. So that would be 0.00000 whatever, 4. Be 4 to 6 decimal places. So that's a very small number. R is just saying, oh yeah, that's between 0 and 0.001. So 3 stars is saying that this variable is significant at the 0.1% significance level. 2 stars would say that it's significant at the 1% level. So that's like you reject the null hypothesis at 1% significance. And similarly, 1 star is 5% significance, a dot is 10% significance. And if there's nothing there, then it's not significant at the 10% level. Hypothesis tests. Let's use this estimated model to test the hypothesis that the returns to education are 0. We already did it. We just did it. Let's go through the work anyways. The null and alternative hypotheses are: the null hypothesis is that the returns to education is 0. The alternative is just saying it's not 0. The t-statistic associated with this test is, hopefully this is familiar by now, we take the estimated value, that's 0.8128, we subtract the null hypothesis of 0, and then we divide by the standard error, the estimated standard error for B on education. And that number is right here. See, this column is standard error. There's the estimated standard error that goes in the denominator of the test statistic. Okay, so we have the two numbers we need. We just need to divide this 0.8128 by this 1.0869. We can do it in RStudio if we want. We don't have to whip out our calculators. Let's just copy and paste this command. There's my test statistic, just a simple division. And let's look at the value for this number. It is right here. If you can see where my mouse is hovering, it's 0.74781. Oh, that is the same as this number right here. So RStudio is automatically calculating all of the tests that the beta is equal to 0 for each one of these variables. This is something that will be done by all regression, all statistical software, whenever you run least squares. It will automatically test the significance of each one of those variables, because this is an important thing to know. Do the variables matter? Well, it looks like all of these variables at the top have no effect on wage. We fail to reject the null hypothesis that their effect on wage is 0. Now, we already know what the p-value is going to be for this test statistic. It's reported right here, 0.45491. But let's obtain the p-value ourselves anyways, because you might want to do a different test. You might not always be testing that the estimated beta is equal to 0. If you were testing some other number, then this is what you would need to do. You would need to calculate the test statistic yourself and come up with a p-value. So I'm not going to spend too much time on this. But we need to know the degrees of freedom from the t-distribution. And the way we get that is by taking the sample size, 534, and we subtract the number of betas that we have estimated. So we've estimated, it turns out, 17 betas, including the intercept. I could get that number by counting all of these rows. I could count all the variables in the regression. There's 17 of them. I could also just look down here. So the summary is going to tell me how many degrees of freedom we have in the model. The degrees of freedom is the sample size subtracted by the number of betas, that we estimate. Okay, so we have 517 degrees of freedom, and that is the number that we need in the t-distribution to find our p-value. Now, our p-value is found by getting a probability, p, from the t-distribution. There's the t right there. And what number am I going to use? Test 1. So that's the t statistic that we calculated. And then over here, I'm going to put the degrees of freedom. Finally, I multiply by 2 because it's a two-sided alternative hypothesis. Let me copy and paste that command and run it. So we're just getting an area under the t-distribution with 517 degrees of freedom. The area is to the right of 0.747, the value of our test statistic, and the area that we found is about 46%. So that's telling us, well, that's a large p-value. That's telling us that we should fail to reject the null hypothesis. And again, notice that this p-value right here is identical to the p-value up here. R has already calculated it for us. Okay, well, that is it for this lab. I hope that it was not too painful for you guys. And on that note, I will end.